try and share my screen. Thanks for coming, folk. I appreciate it. I also have to work out screen sharing. There we go. There's a big button that says share. That's probably it. So I'll make
it have worked.
Sorry? Has it worked?
It seems to have worked, yes.
Okay, great. So I'll make the PDF of the slides available afterwards. I do like it if you ask questions. If there's anything that's not clear, you want explaining, or any questions at all, pipe up and I will be happy to answer them. And the topic is closures, decorators, and generators, which is essentially functional programming with Python and stateful iteration. What do I mean with this? Well, we will get to it. Okay, so I'll be doing the examples in idle. And I'll go back to the slides as soon as I find out where they are. Here we go. Okay, so functional programming. What is functional? Functional programming is programming with functions. Prior to object-oriented programming, we had procedural style programming, which is really just functions or procedures and data structures. And you can still do that fine in Python. But nowadays, what we tend to mean by functional programming is languages like Haskell and OCaml, some of which are pure functional languages. So they have no side effects, which makes, a side effect is something like reading or writing to a disk or printing to the screen or using the network or a database. And that makes them very hard to use for real world tasks. But functional programming is particularly, and Python won't stop you doing pure functional programming, but it doesn't enforce it. And you typically have slightly different data structures for higher order function, for pure functional programming, because you have no mutable state. So functional programming in Python is really what we're talking about is higher order functions and closures. And higher order functions is just treating functions as objects. And closures are functions that return functions. And it's an incredibly powerful technique. I know we have a bunch of decorators in the code base already. I've seen some of them. So a lot of this will be familiar to you. But it'll be nice to get some of the principles clear. So higher order functions are functions that take functions as arguments or functions that return functions. And Python does both. So let's look at functions that take functions. Why might you want to do it? So here we've got two very similar looking functions. One is sum of squares, one is sum of cubes. They don't both take an iterable of numbers. This is a map reduce operation. We're reducing the input iterable to a single value by looping over it and mapping an operation to every number in the sequence or the iterable of nums. So in sum of squares, we're squaring each number and adding it to the total. In sum of cubes, we're cubing each number and adding it to the total. And you can see there, those functions are really similar. There's a lot of duplication. How can we reduce this duplication? And one way we can do that is to generalize the function. And instead of just taking an iterable of numbers and hard coding the operation, we can write a very similar looking function that has all of the duplicated code. This is sum map. So the rest of the code is really similar to what we saw before, but it takes as the first argument a function, also takes an iterable of numbers. We start off with 0. It loops over the numbers, and instead of performing a hard-coded operation, it applies the function to each number. And so here we can write a square function, very simple function. We can pass that in as the first argument, and that's our sum of squares. And you can imagine how trivial it would be to then generalize that to write the sum of cubes using the same technique. So there's a function that takes a function as the argument, as the input. And don't forget, of course, this works because in Python, everything is an object. My mantra in programming, so those of you who were there last time will remember, everything in Python is an object. Every object has a type. You can only perform operations appropriate for the type. Operations are methods and things like addition and sum. So the only really appropriate thing you can do with a function is call it. But function is an object. So a quick refresher on functions, it's the def keyword, then you have the function name, then you have the function signature, and then inside the function you have the body of the function. And this is actually what Python does is there's kind of two steps. When you execute this code, Python executes the definition to create the function object, and then it's actually an assignment. After the function object has been created, the name of the function is bound to the function object. And if we look at the type, there's a custom type written in C, the function type. There's a lovely standard library module that has a whole bunch of these living inside it, if you need to access some obscure types. So there's an example of MapReduce, mapping an operation across an iterable. So for such a simple function, having to define it first and give it a name is a bit bulky, unwieldy. Probably most of you are familiar with lambdas. Who's used lambdas and is familiar with the lambda syntax? I can see Ashley nodding sagely, and John and Paul. I would have expected Paul. And Vincent as well, and Hector. Great. All right, well, let's have a quick refresher. For those who might not have heard of it, here we've got a function a function called square, takes parameter x, the body of the function is return x times x. So this is a statement. We can't put it in line. Suppose we've got another function that takes an argument. I can't define a function here because it's a statement, it's not an expression. What has to go here is an expression. An expression is something like 14 times 4 or obj.method. Those are expressions. They can be evaluated and they evaluate to an object. But statements like the class definition statement, they can take up multiple lines. So a typical function definition is the function definition statement, and the body of the function can contain multiple statements. But this function is doing something really simple. Essentially, the body of the function is this expression x times x. So here, if we look at square, you can see that the name is inherent, is part of the function. We can use inspect.signature. Inspect is another hidden gem of the standard library that I'm a big fan of. Lots of introspection stuff. And we can see that a square is a function that takes one argument, x. We can also write the function as a lambda function, and a lambda function is an expression. So you can put it anywhere that will take an expression. So here is our square function. And this is exactly the same function written as a lambda using the lambda keyword, has nothing to do with lambda calculus, confusingly enough. They're anonymous functions, they don't have names. And you can see this is the big difference, the only significant difference between this function here and this function here, square. Wish I was using a real mouse at this point. I haven't quite got around to it. The only difference is this function knows its name. The name is part of the function, and this function doesn't have a name. It's an anonymous function. Other languages like C# have much more capable anonymous functions. You can have multiple statements within them. Because of the Python indentation syntax, we're limited to a single expression. So the lambda keyword is what tells Python we're creating a function. Then we have the signature, and you've got the full power of Python signatures. So we can have x. How do we say that's a positional only argument? Something like that. I think that's a valid Python function signature now. Probably put this the wrong way around.
Slash is giving me the frightness.
Is it the /? Ah, whichever one it is.
Underscore maybe?
No, it's no underscore. You use underscore to signify an unused parameter. There's a way of signifying positional only arguments, and I never do it. So forget about it. But I'm pretty sure that star is correct for the keyword only argument. No, it's not. We're not going to spend any time on this. Let's go back to x times x. You could there's now Python syntax for positional only arguments and keyword only arguments. And it's sometimes positional only arguments are not terribly useful. They were added into the language for reasonably esoteric languages, but for reasonably esoteric reasons that I won't go into. But keyword only arguments are pretty useful. A parameter that can only be passed as a keyword. And I still can't remember the syntax. Okay, so lambda x times x, that's exactly the same as this function here. Doesn't have a name. If we assign a name to it, we can see it's a completely normal function object. It's exactly the same as the other function, but it's we're limited to a single expression. What happens when we call it is this expression is evaluated and the result is returned. There's effectively an implicit return here. So lambdas are helpful where, for example, in this example, the function is so simple. In the previous example, you see the use of square. And it's a good name, so you probably know what it does. But you kind of have to then jump backwards in the code to see what it does. Whereas using the lambda puts the code in line, you can see what's being done. And they're useful for callback functions where you're maybe wrapping an event handler or something like that. So lambdas are frequently useful. The Python community tends to look down on them. They can be a little bit unreadable. Don't use them to create unwieldy functions. Just create a function and give it a name if there's any complexity to it. So this is functions that take functions as input. It's the less interesting half of higher order functions. Here's an example of using lambdas for partial application. Another aspect of functional programming, and something we see in Python if we write a class, give it a method, by using specs.signature. This was part of the last session I did. We can see that foo.method on the class object. It's a function. It takes self and x as parameters. That's how you define instance methods. If I instantiate foo, what we do is when we look at the method in spec.signature, we see that looking it up off the instance has transformed it into an object that only takes one parameter, and self is already bound in. Is already bound into that object. F.method. It's a bound method. Self has been partially applied to the function. The first parameter has been applied. So the example in this slide has a distance function. Given two numbers, it returns the absolute value of x minus y, the distance between the two numbers. And suppose you were frequently having to work out the distance from 10. We could bind in that first argument to distance. And so create from a function that takes two arguments, partially apply the first argument, and create a function that only takes one argument. And there make a reusable distance from 10 function. And if that's something that you find yourself tempted to do, functools.partial has an implementation of partial application available. Nice simple use of lambdas there. But let's look at closures, functions that return functions, and they are very much more interesting. And let's start by looking at variable scope, the difference between local and global variables. What's going to get printed out? What's going to happen when I call this function? I might expect Paul to know this one. Let me put it back on screen. Anyone got an idea what's going to...
Is it just going to error?
Ah, well done, actually, yes. Unbound local error, and it's a confusing error. If we have time, at the end of this session, I'll take you through the 4 most confusing error messages in Python, and that's the 4th most confusing one. Unbound local error, cannot access local variable x where it's not. What does that mean? X exists as a global variable. If I just write a function, it will happily print 10. So what happens is whether a variable is global or local. Python is a bytecode compiled language like C# and Java, but we tend to call those compiled languages because .NET has the ahead of time compiler, DLLs have assembly compiled into them, and Java has the world-class hotspot JIT. Whereas with Python, the bytecode is interpreted in the interpreter loop in the Python engine. Python runs as a process, and there's a huge switch statement which is called the interpreter loop, and the switch is on the bytecode, and it's a stack-based machine, so there's a stack of internally as well. So there are 2 interesting things that I'm aware of that happen at bytecode compile time, and one of them is whether a variable is global or local, because the bytecode for looking up and changing a local variable is different than the bytecode for accessing global variables. So if a variable is assigned to inside a function, that's then a local variable. So this print x first, it tries to look up the local variable, but the local variable has not yet been assigned to, so we get this unbound local error, which is a subclass of name error. As you can see from this function, functions can access global variables. And if you want to write a function that changes global variables, of course, global variables are bad. We all know that. There was actually a court case, I think it was Toyota, but I might be maligning them horribly, where their automatic braking system would sometimes fire erroneously, just braking suddenly and causing accidents. And as part of the discovery for the case, they had to release the source code, and it was found to contain thousands of global variables. And the judge ruled that because the use of so many global variables was so far from any reasonable standard of programming, that nobody could possibly work out what that code did and whether there was a bug in the code, and therefore they had no defense. So global variables are bad. Use objects and make the objects configurable, store the state on the objects, pass through a context if necessary. Okay, global x equals 7, print x. So this declaration, global x at the start of the function, this tells Python that when we assign to x, you can use a global variable, you can read a global variable without the declaration, but this tells Python that the assignment to x is going to change the global variable. So now if I call a function, it prints 7, we'll find that the global variable has actually changed. And because this is determined at bytecode compile time, this is effectively a compiler directive. It's used by the compiler to know which bytecode to generate for this assignment and this lookup. Okay, so functions that define functions, closures. Factory functions, we sometimes call them, functions that build other functions. If you've used name tuple from the collections module, that's an example. That actually builds classes. It's a function that builds types, but it's one example of a factory function. So got a function add, and we're kind of going to look at partial application again as the example for this. Suppose I very frequently need to add the number 7 to things, but I also frequently need to add the number 6, and I frequently need to add the number 5. So what I want is some way of making specialized adder functions that will do these additions. I can create a make adder function that takes the X parameter. So when make adder is called, every time a function is called, a new stack frame object is created. Actually, it will probably be taken from a pool of zombie stack frames because they're quite expensive. So whenever a function exits, the stack frame is kind of kept around to be reused. And the stack frame has a pointer to the bytecode for the function object, a counter as to where in the bytecode it is, and also an array for the local variables. So local variables, their lookup and assignment, the bytecode is actually compiled to array lookups, and they're faster than global variable use. They used to be local variables used to be the fastest variables, with global variables being slower. They're a dictionary lookup, and built-ins being even slower because there was a fallback. But I think Python 3, maybe 3.11 or 3.12, introduces, if you're not shadowing your built-in variables, they're fastest of all now. So there are optimizations being applied to Python. Python is gradually getting faster. Okay, so when make adder is called, we get a new stack frame with a new set of local variables. That's how every function call has different local variables, and the parameters, they all become local variables inside that stack frame. So when we call make adder, X is a local variable. And then let's have a function adder. The new function takes one parameter. And then make adder is going to return the adder function. So this is a function that has an inner function. So we've been talking about scopes. We've been looking at the global scope. That's a global variable. X here, this is a local variable. This is the local variable. That's the local scope. Here we have an inner scope. We have nested scopes. So when we call make adder with 7, it's going to build a function for me that adds 7 to things. You can see the name here is a bit weird. It comes out of make adder.locals, and it's the adder function. And it's a function that adds 7 to things. And I can make an add 5. And of course, my add 7 still works. So this adder function, let's do inspect.signature on add 7. It's a function that takes one parameter y, yet when I call it, when I called make adder with 7, the value of x was 7, and it returned this function that takes y. And then when I call that function, it still has access to the value of x from the point it was created. So what we say is this inner function here, because it uses the local variable x, this function closes over the variable x. That function is a closure. And in fact, you can see that's actually, like a lot of Python, the internals are exposed and accessible.
Yeah, so is there any opportunity to change this value inside this?
Right, so the answer always used to be no. Paul Graham also always used that as an excuse to prove that Lisp was better than Python. And then somewhere around Python 2.6 or 2.7, Guido got fed up with this and added a non-local variable declaration so that you could change that. But there aren't that many use cases for it. And Guido actually said the main reason he added it was so that Paul Graham would stop being able to say that Python was just an inferior version of Lisp. So there is a non-local variable declaration. You can have functions that return. So I'll show you that shortly. Here's another simple example. We've got a greet function that takes a name. It builds an internal doGreet that closes over the variable name through the F string, and it returns a greeter function. And whenever you call it, it has access to the original name. But we can use this greet function to build multiple greeters. So the inner function refers to a local variable from the outer function. It still has access to it. So that inner function is a closure. DoGreet closes over the local variable name. An important point is that they will only DoGreet here. It only closes over the local variable name. If there were other local, so it keeps. If you go back to here, there's a closure. There's a cell object. I think it's got cell contents. There's this level of indirection, so they can actually be changed. But it's only closing over variables that it's actually using. It's not going to stop anything else getting garbage collected. It's very rare to mess around with these values, but it's interesting to be able to look at them.
Would you have similar behavior with... Sorry, go ahead, Paul.
I was going to say, what happens if you change that cell content to something else? I mean, I know it's double underscore and you shouldn't change it, but
no, it's a dunder. So the convention is anything with a single leading underscore is private. But these dunder ones, like dunder, so double underscore closure, double underscore, a bit unwieldy to say. So a lot of us say dunder closure and dunder dicks. They're internal to Python. They're used by Python, but they're not. It's not always inappropriate to mess around with them. However, I think you'll find that they're read-only. Oh no, let's have a look. It's not read-only. Since the introduction of non-local, since the introduction of non-local, they've become mutable. They used to be immutable, and there used to be a hack to change them via C-types, the C-types module. But since the introduction of non-local, they've become mutable. So you can actually mess around with the contents of closures. I don't recommend it. Use the non-local keyword instead.
So it's not relatable then.
Sorry? It is. It is.
The closure.
Yeah, look, I changed the cell con. Add 7 was storing the local variable x that it closed over, and that was stored in the closure cell contents as 7. When I changed the cell contents, add 7 now adds 67 instead. I'll show you how you would do that actually. Let's say we've got a counter. See, I don't think I've got a slide on this. So we've got an increment function, non-local, C plus equals 1, turn C. So I've got an increment function, and see how it's declaring non-local C, because that plus C plus equals is exactly the same as C equals C plus 1. C plus it, so it's it's a lookup and an assignment. So normally that would create a new local variable C inside Inca, but non-local here tells Python this variable C is a local variable, but from my enclosing scope, or one of my enclosing scopes. And then I'll create a decrement function as well. Non-local C. So you can create closures that communicate with each other through non-local variables. Return C, and now counter returns. I don't think I've ever used non-local, but it's there. So Inca deca equals counter 10. Ah, I made a typo. So those two variables created as closures inside a counter are sharing that that variable C and are able to modify it through the non-local keyword, which again is another compile time directive. Is that clear enough?
The scope of that C isn't beyond the scope of count, is it? I'll
No.
phrase that as a question.
You
can't type C now.
Basically,
yeah, exactly
so when we call counter, that creates a stack frame. The code is executed inside that stack frame, and if we were looking at exception handling, I might show you sort of stack frames that create stack frames, and you get, you know, when you get an exception, your exception handling can be at stack frames well above the function that you're being called, or if that exception is unhandled, you get a traceback. So stack frame, a lot of your running state in Python is this linked chain of stack frames from a function call that's called a function call that's called a function call. But what happens is we have a stack frame. Inside that, the incra function and decra functions are created. Those both have are closures, so they have this done to closure attribute, and they effectively share that cell contents through the non-local keyword. So once we've called counter and that's finished, that stack frame goes away, but the variable they're using stays. Incur. I mean, this is a bit of a cheat. It would be true anyway, but. They're the same thing. They're sharing that variable. So this way, we've created a couple of functions, and they have some shared mutable state between them through that non-local variable. Some shared mutable state. I did say that, didn't I? And closures only close over the variables they're using. In this example, get result closes over result. So when add exits, this is delayed evaluation, X and Y will be garbage collected, but results will be kept alive. Everyone happy with that? Oh, I do have an example of non-local. There we go. You can have functions within functions within functions. We're going to have a look at that when we look at decorators. And functions can return multiple closures, like the incodecor example that I just gave you.
I have a question. So you said, obviously, global will make Python understand that the variable is global, and then non-local checks like just the scope above. What if you have many?
Just one. You can have a few levels of nested scopes. If you declare non-local C, Python will essentially check all of the enclosing scopes one by one and pick the first one it finds.
Okay.
So it can be multiple levels of nesting if you want.
I cannot really think of a use case, but I was just.
Well, when we do, we're going to have a look at decorators next, which are a very practical use case for closures. And when you write decorators that take arguments, we're going to use 2 levels of nesting.
Yep. Gotcha. Thanks.
So there's a few reasons to use them. They're considered an aspect of metaprogramming because you write functions that build functions. And the important thing, I guess, is that because they close, we can have functions that take arguments, and every time you call a function, these local variables can be different. And the inner function, it closes over the local variables at the point at which it's created. So they encapsulate the state from the point of which they're created. So you can write functions that build other functions specialized to perform different tasks, slightly different tasks, based on the input you give them. And again, collections.nameTuple is an example of how it builds related but different things from the input that you give it. Closures are great, where you're writing a bunch of functions that are very similar, but with slight differences. You may well be able to create a factory function that can build all of them for you. So decorators, this is a practical use case of closures, and it's about wrapping functions, functions that wrap other functions. So let's go back to our add function. This is probably, yeah. Let's suppose we want to add some logging to this function. We want to know when it's been called. So I can write a function, say logged add. It takes x, y as parameters, does some logging, calling add, and then it delegates to the add function with x and y. And now when I call logged add, I get this extra logging output every time I call it. Now, don't forget, we talked about higher order functions, functions that take functions as arguments. We can generalize this. We can write make logs. We can write a function that will add logging to any function. So we'll write make logged will take a function. We'll define an inner function. We use the star args and star quargs syntax. This means the function can be called in any way. Star args means any number of positional arguments, including none, which will be collected together as a tuple. So if there are no positional arguments, args will be an empty tuple inside inners. And star quargs means the function can be called with any number of positional arguments, which will be collected together as a dictionary with keyword mapping to the value. And again, if there are no keyword arguments, quargs will be an empty dictionary. You can call them whatever you like. If you haven't got a better name for them, I mean, sometimes this is options or something like that, but args and quargs are well established as a convention. So we can do our logging. We can use the function name in an F string. And then we can delegate to the original function, and there's this corresponding syntax, unpack a tuple into the function calls as positional arguments, and the star unpack a dictionary into keyword arguments. And this function, this will have no idea that it was called in this way as far as it's concerned. It's just been called with a certain number of positional arguments and keyword arguments. And this is key to writing many decorators. And then we'll return the inner function. So I can make our logged add by calling make logged and passing in add as the function. That gives us this inner function. And it adds our logging in and then delegates to the original function. So here, make logged here is wrapping a function. It's wrapping the function call, but adding in some additional behavior. And this is what decorators do. And it might turn out, and it very often turns out, that when you're wrapping a function, we only want the logged version of add. We don't want the unlogged version. And so what you can do is you can do add equals logged add passing in add. So when you have an assignment like this, there's two sides, the left-hand side, the right-hand side. The right-hand side is evaluated first. So our add function is looked up, it's passed in to the logged add function, and then the name add is rebound to point to whatever comes out of the logged add function. Logged add. Oh, make logged, that's what it should have been. That was confusing for a second. So now the name add points to my logged version, and I don't have a direct reference to the unlogged version. And that's what decoration is. So let's go back to the slides on this. Decorators are typically built-on closures with an inner function, although interestingly, we have some built-in decorators in Python that are not functions. So here's the logged add example. Here's the wrapped example. And this is where we replace the original one with our wrapped version. So other coded people, anyone who imports add or uses add will now get the logged version. And that's what a decorator is. When you replace a function with a wrapped function, you're adding in extra functionality. You can do it before the function call. You can do it after the function call. You can process some of the parameters, process the return result. There's all sorts of things you can do with decorators. And that process of doing def add x comma y, return x plus y, add equals make logged. That's creating a decorated function. And so we have some syntactic sugar. We have some special syntax for doing this. It doesn't do anything that we couldn't do before. But we have this syntax using the pi symbol, the @ symbol. These two bits of code here, this code here and this code here, are exactly equivalent. What happens when Python encounters this code is first it executes the function definition, it creates the function object, then it calls make logged, passing in that function object, and the name add is bound to whatever make logged returns. So that's what decorators do and how they work. Decorators are functions that wrap functions. And what it means is we never have access in our namespace to the unwrapped version. And there are some built-in decorators, some of which you're probably familiar with. Property, we're class method and static method. And actually, these aren't functions, these are descriptors. And prior to the @ syntax, which came in Python 2.4, and it's one of my examples of where the community consensus is not always a good thing. The entire community had consensus that this syntax was a bad idea, except for Guido. He did it anyway, and it worked really well. So one of the advantages of a benevolent dictatorship. And the interesting thing is class method, property, and static method are not functions. They're descriptor objects. And so they don't return functions. So they're kind of an exception to the rule that decorators typically are functions that wrap functions. Avoiding code duplication. Again, another aspect of metaprogramming. A very simple one where you've got views in a web application and you want to check, have I got a logged in user? and you've got your view functions. So the first thing you have to do at the start of every function is if request.user is none or equals is none, do a redirect to the login page. And it's only a few lines of code, but it's easy to get wrong and it's duplicated everywhere. And so you can have a decorator that wraps your view function. When the wrapped function is called, it checks whether there's a logged in user. If there isn't, it does the right redirect. If there is a logged in user, it just calls the view function that it's wrapping. So you undoubtedly have used decorators a great deal. They're very handy, and you sometimes see them stacked 5, 6, 7 high, particularly in web applications, and it can get a bit crazy. So this is a different kind of decorator, and slightly different. The only difference is that this does something after the function it's wrapping is completed. So this is timing a function call. It's wrapping func. It's got this wrapper function. It takes the time, it calls the function and gets the result, gets the end time, prints how long it took, and then returns the result. So we're not just doing something before the function call, we're doing something after the inner function call as well. So decorators are very flexible about what you can do with them. However, this approach has some problems. And we're going to look at multiple decorators, decorator metadata, and decorators with arguments. And I'm going to look and see how we're doing on time. What's the time? I can't see on this machine. Oh, we're nearly. Yeah, we're probably not going to get to generators, so I'll do that. I'll follow that up in a iteration. And generators are great. Okay. In this example, which decorator is applied first? If you stack your decorators like this, is foo applied first or spam?
Spam.
Yes. They're like multiple layers of wrapper around a present. So spam is the first wrapper. So in this case, add is called with spam. Whatever spam returns is passed to bar. Whatever bar returns is passed to foo. And this particularly matters where you use property and class method and static method. Because these are descriptors, they don't return function objects. And I've waffled far too much. That's why we're not going to make the time. Sorry about that. If you're putting decorators on methods and you also want to use class method, property, or static method, they have to go at the top. They have to be the last applied decorator, because otherwise, if property is first, what comes out of that is a property object, and that can't be used by any decorator that's expecting to wrap a function. So let's do decorator metadata, which is really important, and see if we can get decorators that take arguments in as well. So functions have metadatas, they have their name, they have their doc string, they have their signature. You can look at that. That's really important. If I do help on add, it says, what it tells me is it's an inner function that takes star args and star quarks. All that useful metadata has gone away from the function. The signature has gone, the name. You can also attach attributes to functions. You can tag functions with attributes. Functions have a dunder dict that was added specially so that you could do this. So you can have a pipeline of tagged functions. It's a useful thing to do sometimes. So losing the metadata is a bad thing. You can either manually copy it across yourself, which you shouldn't do. What you should do is you should use functools.wraps, and wraps your wrapper functions. And what it does is it copies across all the metadata for you. So whenever you're writing decorators, always use functools.wraps, and that metadata is not lost. So important thing to do. From functools import wraps. Wraps your wrappers. And the last thing I think we're going to have time for, decorators with arguments, sometimes called decorator factories. You'll have seen decorators that take arguments probably. So a decorator is a function that takes a function and returns a function. So a decorator factory is a function that takes arguments and returns a function that takes a function that returns a function. Got that? The decorator factories are functions that take arguments and they return a function that takes a function and that returns a function. Essentially, they're functions that build decorators, so you can customize the decorators that you create. So this code here at decorator XYZ is effectively calling decorator with XYZ. This gets the decorator itself, and the decorator is used. So it's exactly equivalent to this code. And it's also exactly equivalent to this code. First call the decorator with XYZ, that gets us the decorator. So decorator factories is a useful name. Decorator here is a decorator factory. We call it with the parameters XYZ, and it builds a decorator for us. And to do that, we have two levels of nesting. We write a decorator factory that returns a decorator. So if you look at this on the screen, it looks perhaps a little bit mind-bending. We've got two nested scopes. Log message, this particular decorator factory allows us to customize the log message. So inside is just the original decorator that we had previously, but we've wrapped it with another function that takes a message argument, and right inside the wrapped function, so this message variable here comes from two scopes up, and we can use that message. So we can now use log message to build various different log decorators that with custom messages. So inside log message there is exactly the same decorator that we had before. It takes a function, builds an inner wrapper function, but we've just wrapped it in order to make a decorator that can take arguments. We've wrapped it with that extra outer function. And because decorator function factories build decorators, you can in fact just call them. If we're going to reuse the same one, what it returns is a decorator. So it's the decorator factories build customizable decorators for you. They're factory functions that build decorators. Everyone happy with that? Neither assent nor dissent. That's probably as much as I can hope for. Okay, so there's a couple of points to finish up on the topic of decorators. There are class decorators. Data class is one. It's used a great deal in Gigaclear. And it's the same idea, but instead of wrapping a function, we're wrapping a class. So you apply the decorator to the class. And there is actually a slight difference. The principle is exactly the same, but how they're used tends to be different. Normally, when you're writing a function decorator, it takes a function and it wraps it. It creates a new function and it returns a new function. Class decorators typically modify the class in some way, inspect the class, do some registration to the class, and then return the same class. So they're slightly less common than function decorators, and they're typically implemented slightly differently. So here's an example, logged get out, a lot of logging in these examples. Done to get attribute is the magic method, the protocol method used for all attribute lookup. Normally exists on object.done to get attribute. It's where stuff like the descriptor protocol is implemented. It's rare to override it because it's used for every attribute lookup. And you don't, attribute lookup is so common, you don't typically want to make that any slower. But here we're giving a class. Given a class, we fetch the done to get attribute. We wrap that with a custom one that does some logging and reattach it to the class and return the same CLS object. So it can now be used like this as a decorator on the class. And any attribute lookups on instances of that class will now be logged. So a way of adding diagnostics to that class. This is the implementation again. Logged getAttr is a function that takes a class and returns a class, and inside the body it's modified the class. The class is just an object. We can look up attributes of it. We can attach attributes to it because everything is an object. Everyone happy with that?
And what about the metadata of these functions in this class?
Metadata. So we don't need, because we're going to generally return the same class, we don't need to worry so much about. We don't need to use functools.wraps like we did with decorator functions. There is an exception which we recently discovered in Sphinx, that data classes, when you use slots equals true, they regenerate the class and they actually return a different class. And the trouble with that is that supercalls, again, rewritten at bytecode compile time, so they've got the class hard-coded into them at bytecode compile time. So the fact that they regenerate the class means that super no longer works, or super without arguments no longer works when you use slots equals true in data classes. You have to use the 2-argument form of data classes, and that's a problem that the attrs library also encountered and fixed. So that's going to be fixed in Python 3.12, I think, or 3.13 maybe. So in general, you don't, because you're returning the same class object, you don't need to worry about metadata. I mean, this function here, nobody's going to look up the get attribute and look at the doc string on dunder get attribute. So, you know, I mean, maybe this should use functools.wraps, but no one's going to care. So because it's applied at class creation time, one of the things that we used to use to customize class creation was meta classes. And class decorators can be used to do a lot that meta classes used to be used to do, and you shouldn't use meta classes. The thing is that class decorators aren't inherited. If we create spam class ham that inherits from spam, the class decorator won't automatically be applied again. So if you want to customize subclasses, you can use the dunder init subclass method. And there's a really nice example of that in the data class envloader Gigaclear project that uses dunder init subclass. You create a parent class, and dunder init subclass will be called every time a subclass of that of parent is made, and you can even pass in parameters to it to customize how the subclass is made. And that further reduces the need for meta classes. And I think that's probably about all we've got time for. Anyone got any questions? I'm sorry we didn't get to generators. We'll have to do another installment. I have loads more I want to talk about. You lucky people. All right, thank you very much. I'll make the recording.
Thanks so much. That's brilliant. Thank you.
Thank you, Michael.
Thank you for doing that,
Thanks.
Michael.
Thanks, Michael.
Really good. Cheers.